So in today's video, we're going to be looking at variables, expressions, and exponents, getting ready to move into some more algebra. And so this kind of comes with the prerequisites of the previous few videos that we've been looking at, where we've looked at addition, multiplication, subtraction, and division, and then just place value, how to identify which place we're looking at, and then rounding to different places. So those are kind of the prerequisites before you can start moving into this video. If you have a good foundational understanding of that, this video is for you. So, what are variables? When we're thinking about variables, we want to be thinking it's representing some unknown quantity, number, or amount. And so we use variables to allow us to represent something that isn't known at the time, and then we can ultimately solve for that if we can find other pieces of information that allow us to. And so right now, just having a look at a bit of an example, we can see two siblings here in the table. We've got Lucy and Sam. Sam's Lucy's older brother, and Lucy is 12 years old currently. And so if Sam's 15, then you can see there's a 3-year age gap between them, right? And so at 20 then, Lucy would be 3 years younger. And so when Lucy's 20, Sam will be 23. When Lucy's 35, Sam will be 38. And so you can kind of see that there's this pattern forming where Lucy's age will be 3 less than Sam's age. And so we can represent Lucy's age generally as an X, right? So it doesn't matter what number you put in there, it's always going to be 3 less than Sam. And so if Lucy's age is going to be X, then Sam's age would then be X plus 3. So all that's saying is that imagine I put in 28 as X. So Lucy's 28 years old, therefore Sam would be 31. And so you can see if I look on the left-hand side, X would be 28, Sam's age would be X plus 3. 28 plus 3 is 31, and so we can see that we've kind of represented that relationship using a variable. So generally, when we're thinking about variables, we're thinking about using a letter. And so a variable is a letter that we use to represent some unknown quantity or number. And usually this variable or number is something that potentially could change. So in this example, we've got age, which changes each year. So our age is always going to go up. And so therefore we can represent relationships using a variable to allow and adjust for that change. Another example could be weight. And so you could say that if Lucy's always 20 kilos lighter than Sam, if that held true, then you could say Sam's age was X plus 20 for weight. And so we'll get into a few more proper examples soon, but as long as you understand that a variable is just a letter that we use to represent a potentially changing quantity or number. And so what's a constant then? Well, a constant is just a number whose value always stays the same. And so this could be things like, how many fingers do you have? Well, it's going to be 5. Chances are, unless there's some big accident, that you're going to have 5 fingers, and so that would remain constant. So another key point here is that we have some commonly used letters that we use for variables. And so really a variable could be any letter. You choose them. So maybe if it was a height that was changing, you could represent that variable using H. But the commonly used variables are X, Y, and then things like A, B, and C. The most common will be X and Y though. And so building upon our last few lectures on addition, subtraction, multiplication, and division, we can kind of extend the concept of this notation and how we read things to algebra. And so all we're doing here is representing, rather than using numbers or constants as we call them, we're using algebraic variables. And so for addition, instead of being 7 plus 8, we would go A plus B, whatever they may be. And so that's read as A plus B, and the result would then be the sum of A and B. And so this should be very, very familiar to you, so I won't bang on too much about it. But subtraction, A minus B, the difference of A and B is the result. You can see a few different symbols here for multiplication, and you might notice that we're actually missing the most common A and then the cross or the X looking symbol, so the times symbol, then B. And the reason we don't use that is because X is such a common variable that we kind of don't want to get confused between X's and times. And so we generally use the dot or the bracket format. So A times B, and we still get the product of A and B. And division, so we've got all of the same. The most commonly seen will be fractions. You won't see too much of the actual division symbol purely because a lot of the time it's easier to represent in algebra using fractions. So it's still a divided by b, and we still get the quotient of a and b. So just an example here. So we've got 4 questions. I will do all of them, but I would suggest that you have a quick go first just to make sure that you understand. Some of this should be you should be pretty confident with from the last few lectures. So translating from algebra to words, well, we say the first one is 12 plus 14. B, well, we've got brackets around, which means multiplication. And so we've got 30 times 5. C, we've got the division symbol, so it'll be 64 divided by 8. And then finally, the only one where we've really got variables in there is the last, which is D. And so we get x minus y. So it's the exact same concept, shouldn't be too hard there. So when we're thinking of algebra, we have both expressions and equations. And so we use things like equal signs to separate different expressions. So remembering that an expression doesn't have 2 sides to it. So an expression could be a plus b, or b plus d, or d divided by x, or whatever it is. But there's no d divided by x equals some amount, right? And so an equation would then be connecting 2 expressions. So a plus b equals c, something like that. That would be an equation. And so in general, we have the equal sign, so the 2 lines, and that's frequently used when 2 quantities have the same value. And so we're saying in algebraic terms, if we can have one expression on the left-hand side and one expression on the right-hand side, we can say if they do have the same value that they are equal to each other. So as an example, if you knew that your age was 7 years old and you knew that A also equaled 7 years old, you could say that A equals 7, and that would hold true. So we'll get more into that soon, but just as long as you're aware of that. And so inequalities are basically, we're not saying something is equal, we're just saying that it has some comparison to a different expression. So we're comparing one expression to another based on whether it's smaller than or equal to or greater than. And so we'll get into that in a second. And so ultimately it is used to compare quantities that have potentially different values, so may have different values. So in the first, we have A is less than B. And so we've got this symbol here that I've highlighted, which means less than. And so that means that A is less than B. If we look at the number line, we can see that if we're starting from the left-hand side, A comes first and then we get B. Remembering that number lines go from smallest to largest, from left to right. And so therefore we can see that B is a larger number than A. And so this could be read left to right, or we can read it right to left, as long as we're thinking of the symbol pointing to the other value. So as an example, A is less than B. We could also flip the symbol and flip the whole inequality and say B is greater than A. These have the same value. And so the next example, we have the greater than symbol. So A is greater than B, which is the same thing as B is less than A. And so if you look at the number line in this example, if A is greater than B, we expect A to be further along the number line to the right. And so we can see that it is. Finally, we can also see these symbols here. So we have a little line underneath. And what these mean are that it could be less than or equal to. So it's using some comparison where we're including the value, saying that it could be equal to that expression. It could also be less than. Or alternatively, it could be greater than the other expression, but it could also be equal to. And so now just to summarize a few different symbols that we used for these inequalities and equalities. The first is just the normal equal sign. And so we're saying A is equal to B, so they have the same value. Then you might see this little sign. And so it's just an equal sign with a line through it. And this basically means not equal to. So we're just saying it's some other value. They're not equal to each other. And so it's read as A is not equal to B. Then moving down the list, we can see the ones we've just touched on. So we've got A is less than B, A is greater than B, A is less than or equal to B, and A is greater than or equal to B. So now just an example where we translate from algebra to words. So for A, well, we've got the less than or equal to symbol in between the two numbers. And so remembering that the left side, the side that's pointed to in this case, will be the smaller side. And so we've got 20 and 35. And so we can say 20 is less than or equal to 35. And so we know in this case that it is less than 35, but the expression holds true. As long as it's one or the other, it's fine to use. And so this one is a little bit trickier. So we have the not equal to symbol, but then we have a number on the left-hand side or a constant, or we have an expression on the right-hand side. So we've got 15 minus 3. So 15 minus 3 is the same thing as 12. And so 11 is not equal to 12. And so we can say that's also a true statement. Next, we have the greater than symbol. And so this should point to the smaller side still. And so we can see that the right-hand side is 10 divided by 2, which is 5. And so ultimately what this is saying is 9 is greater than 5. This is also true. For D, we have the less than symbol. And so x plus 2 is less than 10. And so this one's a little bit tricky, but it's more common what you will see. And I won't show you how to solve it, but all I will show you is that if this expression is true, which it must be if we write it down, we have to use a value of x that makes it less than 10. So the highest value of x that we could actually use if it was a whole number would be 7. So 7 plus 2 would be 9, and 9 is less than 10. If we use the number greater than, like 8, 8 plus 2 is 10, and so 10 is less than 10 would be an incorrect equation. And so we could use 1, we could say x is equal to 2, x is equal to 3, x is equal to 4, all the way up until x equals to 7. After that, we would then be making a false statement. So we've got to be careful there. So in this one, I've got some pictures of some cars. And so we're just going to be using these inequality symbols to represent these expressions. So the expressions aren't numerical in nature. We're doing this kind of qualitatively. And so we need to first determine what the MPG of each car is, and whether that has some comparative relation to the MPG of a different car. And so we're just using the numbers, which MPG is miles per gallon, so it represents fuel economy. So in Australia, this would be kilometers per litre. So we wouldn't be using miles per gallon, but hopefully you can adapt. So it's just about the numbers, really. And so MPG of Prius and MPG of Mini Cooper. So we'd want to go and look at what those are. So the Prius is 48. The Mini Cooper is 27. And so if we just write down 48 on the left-hand side and 27 on the right-hand side, we would need to use one of the inequality symbols that we've just learnt about to represent those two numbers. And so you can think of a couple. You could say greater than, you could say greater than or equal to. If you wrote equal to, you would be incorrect. So 48 does not equal 27. So you could write does not equal to. And so we really have three options here. I would say 48 is greater than 27. You could also write greater than or equal to. Alternatively, you could also write not equal to. And so we will stick with the most common. So we'll be using the greater than or equal to symbols for this. And so the next one, we've got the versor versus the fit. And so the versor has 26, the fit has 27. And so in this case, we can use less than. So 26 is smaller than 27, so we could use less than. Mini Cooper and fit. Mini Cooper is 27. Fit is 27. And so really, we could use greater than or equal to, less than or equal to, or just the equals. And so we'll choose the equals in this case because we know the values. And so we will say that each side of that expression is equal. The corolla has 28 and the versa has 26. So in this case, just to be complete, we'll use the greater than or equal to sign. And so we know that 28 is greater than or equal to. In this case, it happens to be greater than, but it only has to be greater than or equal to, so one or the other. Then finally, we have the corolla versus the Prius. And so from the last part, we know that the corolla is 28 and the Prius is 48. And so we can use less than or equal to. So 28 is less than 48, but it only needs to be either or. So it can be equal to, or it can be less than. And so it is less than, which makes the statement true. So another really important part for algebra is grouping symbols. And so these are things like parentheses, brackets, curly braces. And so really what they do is they separate parts of the expression from each other. And so using the order of operations where we use brackets, or we complete the brackets first. So the further in the brackets are, the earlier we complete them in our order of operations. We'll talk about that soon. But you can know that these grouping symbols, it doesn't matter which one they are, they keep expressions separate from others. And so if we look at this example here, we've actually got the innermost parentheses, then we've got the braces, the brackets, sorry, and then we've got the curly braces on the outside. And so you can see we've used 3 different grouping symbols to separate different terms. And ultimately, this will change the outcome of this equation. And so it's really important that you understand how they work and that in your maths that you're using them correctly to compartmentalize different parts of the expression. And so I've kind of touched on this already a bit in this lecture, but I think it's really important to reiterate on. So very, very key you understand this. So the expression is just a number, a variable, or a combination of numbers, variables, and operation symbols, but no equal sign. So we're not connecting multiple expressions together. And so we're looking at things like 3 plus 5, n minus 1, 6 times 7, x over y. So we're not putting any equality or inequality. And so that's the key difference between an equation. And so an equation is then 2 expressions which are connected by an equal sign. So rather than just saying 3 plus 5, we say 3 plus 5 equals 8. Rather than saying n minus 1, we can use n minus 1 equals 14. 6 times 7 equals 42. X equals 53. Y plus 9 equals 2y minus 3. It doesn't matter what the expressions are. If they're connected by an equal sign, then we're saying that those are 2 expressions put together with an equal sign, which makes it an equation. So now we want to be able to determine if each of these equations or expressions is an expression or an equation. And so the key thing I will put out there is don't stress about how difficult it may look and whether or not you could solve it at this level. It's just about whether there's an equality in there. And so for A, 16 minus 6 equals 10. So equals, we say equation. And so it kind of says it in the equation that there has to be some kind of equality or inequality to make it an equation. And so we'll use EQ to represent things that are equations. So B, 4 times 2 plus 1. There's no equal sign, therefore it's an expression. X divided by 25, no equal sign, it's an expression. And then finally, y plus 8 equals 40. Well, equals means equation. All right. If there's no equal sign, it's an expression. If there is, it's an equation. If there's an inequality, it's also an equation. Simplifying expressions with exponents. So this is actually quite difficult of a topic, but it's important to understand that the purpose of this is to prepare you for algebra. And so algebra has a lot of indices or exponents, and so we're not going to go through everything in the utmost detail in this course. There will be other courses for that. So if you need extra help, there will be other videos that you can look at on the channel. So look at things like index laws, exponents, but this is This video is really going to break it down quite simply and then expand upon that. And so when we talk about simplifying, it doesn't have to be with exponents. Simplifying, it just means to do all the math that we possibly can. And so in the example here, we have 4 times 2 plus 1. Well, we can simplify 4 times 2. We can say that's 8. And then we can do 8 plus 1. So we get 9. And so the simplest form of that would just be 9. And so the expression would be 9. And so just a little side note here. It's better to work down the page. It's also mathematically correct, but I see so many students that don't do it. So if you write each step down, so going down the page, it keeps the working neat. And in my opinion, it's a lot easier to become incorrect if you're not neat. And so I can't impress enough how important it is to just take the extra time. I don't want to waste my time doing messy math and then getting the wrong answer. Even if it takes a few extra seconds or minutes to do it neatly, I then am more confident in my answer being correct, will get marked well, I'll enjoy math more than if I was getting it wrong all the time, and I'll actually be able to learn and continue to get things kind of moving mathematically, as in I'll be able to continue growing and learning harder and harder topics because I'm actually getting them right. I feel confident. And so simplifying in general is very true for exponents. And so what an exponent is it's a way of representing repeated multiplication with the same number. And so here you can see 2 times 2 times 2. We could simplify this into 2 to the power of 3, or 2 cubed. And so that all that means is that if we expand 2 cubed, we're saying 2 times 2 times 2, or we're multiplying 2 by itself 3 times. And so 2 to the power of 3 is the exponential notation. 2 times 2 times 2 would be the expanded notation. And I'm sure that you can see that 2 to the power of 3 is a lot simpler to look at. Maybe not straight away to work with, but to look at, it takes up less room, it's a lot neater, and it's just a lot easier to work with in the long run once you work out how to use index laws. So diving a bit deeper into exponential notation, we can see that we've got a base and an exponent, or an index, or an indice. And so the base is any number below. So when in the last example it was 2 to the power of 3, 2 was the base, 3 was the exponent. And so really, in general, a to the power of n just means we expand the a out, multiplying it by itself n times. And so if this was a to the power of 10, a would be multiplied by itself 10 times. So importantly, we can read this as a to the nth power. So as an example, 10th power, 11th power, 12th power. And so we always say it like that, except for when the exponent's 2, we have the word squared. So we would say a squared. And when it's 3, we would use the word a cubed. And so you will also see these buttons probably on your calculator. Whereas if you have a larger exponent, you will have to manually input the exponent into a function on your calculator. So a few examples. We want to write each expression in exponential form. So remembering in the last example, we had a, which was the base, raised to some power. And so 16 here happens to be the base. So in expanded form, a is just multiplied by itself over and over again. And so all we want to do is we want to write the base, which is always going to be the number there, or letter. And so we've got 16, and now we just want to count how many 16s are multiplied together. So we've got 1, 2, 3, 4, 5, 6, 7. And so we would say 16 to the power of 7. And so we can go back and forth between these. And so it is bidirectional, and we'll go into expanding them in a minute, but that's how we do it. So 16 is the base, and then 7 is the exponent. In the next one, 9 would be the base, and we just count the 9s to find the exponent. So 1, 2, 3, 4, 5. So you should be picking this up pretty quickly. If not, I'd suggest to go and have a look at some of our other videos on index laws, and we'll have a lot more examples there. So same thing for variables. Don't get frightened by the fact it's not a constant. we just look, what's the base? What's the number that's multiplied, or the number or the variable that's multiplied by itself? And so x is the base and 4 is the exponent. Have a go at D by yourself. I'll work through it now. So we've got A is the base and we've got 8 as the exponent. So now doing the opposite, we want to write each exponential expression in expanded form. So remembering that 8 in the first example will still be the base, right? And so this will still be multiplied by itself the amount of times that are in the exponent. So in this case, we'd have 8 times 8 times 8, and this would happen 6 times. And so that would be the expanded form of 8 to the power of 6, or 8 to the 6th power. And so then x would be the base, and we'd multiply it by itself 5 times. So pretty simple, but important to understand. So now moving on to some simplifying. So remember, simplifying means doing all the math possible. And so in expressions where there's just numbers and not variables, we'll always be able to just solve them. And so 3 to the power of 4, obviously you could do this on your calculator. I will show you a way by hand. In your head, you can probably calculate some as you go, but what we can do is we could say 3 to the power of 4 in expanded form is 3 times 3 times 3 times 3. And so if you're able to do multiplication like that, we could say 3 times 3, which is 9. So then this would become 9 times 3 times 3. We could then say 3 times 3 on the right-hand side, remembering that we can have that commutative property of multiplication, where we can multiply them all around if they're all multiplied by each other. And so we could say that this 3 times 3 is also equal to 9. So then we get 9 times 9, which I know is 81. And so 3 to the power of 4 is equal to 81. So moving on to order of operations. So we really need to get this through our heads very, very clearly. And so as an example of what can go wrong, we've got this 4 plus 3 times 7. And so we've got two potential outcomes of this one problem, or this one expression. And so on the left-hand side, we can see we do 4 plus 3 times 7. And then we add the 4 and the 3 together, and we get 7 times 7. So just to color code that, this 7 is this 7, and then this 4 plus 3, this 4 plus 3 becomes this 7. And so ultimately we get 7 times 7, which you should recognize is 7 squared, is equal to 49. Alternatively, on the right-hand side, we have 4 plus 3 times 7, same expression, but then we say 3 times 7 is equal to 21. And so this 21 is there. And then this 4 is this 4. And so then we get 4 plus 21 is equal to 25. And so two completely different answers. We've got 25 and 49. Which one's correct? So we can't answer that question until we look at order of operations. And so we have BOMDAS or PEMDAS or BODMAS, or there's a bunch of different ones, but effectively it's just our way of remembering from left to right what we do in an equation or an expression. And so with BOMDAS or PEMDAS, which are the main ones, we would have brackets and or parentheses. Basically any grouping symbols come first. And so we would simplify all the expressions inside any parentheses, remembering that we still have to do BOMDAS or PEMDAS inside each bracket as well. So that can be quite tricky. And so we work on the innermost bracket or parentheses or grouping symbol first. So then we have orders or exponents. And so we're just simplifying all the expressions that have exponents. So things like powers, exponents, and roots. Really important to include roots as well. Then we move to multiplication and division. And so we perform it left to right. any multiplication and division. They're equal priority, so it doesn't matter. Whichever comes first from left to right, we do that. And then the same thing with addition and subtraction. So they're also equal priority. And so in general, we can see that this goes from left to right. So we just want to think brackets, then orders, then multiplication or division. These are grouped. So you can do either or. So it's just left to right. And then same thing with addition, subtraction. They're also grouped. So we also go from left to right. PEMDAS is the exact same thing, but instead of B, we've got P, which stands for parentheses. And then instead of O, we have E, which stands for exponents. I would highly recommend writing this down until you have this internalized. So now we're able to work on our expression from earlier. And so let's start A. We've got 4 plus 3 times 7. And so before we might have just gone left to right and done 4 plus 3 and then multiplied that by 7 and we got 49. From BOMDAS, we'll write it up here so we can remember it. We know we have to go brackets first. Are there any brackets? No, there's not. So we can then move on to orders, so exponents. Do we have any exponents or roots? No, we don't. So now we move on to multiplication or division from left to right. So scanning from left to right, I do have multiplication. And so I need to calculate that first. And so that would be 21, then 4. Now I look 4 plus 21, well, that's addition and subtraction, which comes next. And so I can calculate that straight away. And we ultimately end up with 25. And so you can see that that would be the correct. 49 would be an incorrect answer. So B is very similar. The only difference here is we've got brackets now. And so we've got 4 plus 3 multiplied by 7. And so what this means is that if we've going from left to right, we have brackets first. So we need to simplify the insides of the brackets first. And so here on the right-hand side, we have 7. We can't simplify 7 any further. So we need to look at the left bracket and we can simplify that. And so we get 7. So 4 plus 3 equals 7. And so now we have 2 brackets, which means that we're multiplying together. There's nothing else we can do. And so we'd go 49. So you can see how important BOMDAS or PEMDAS or order of operations in general really is. So just a bit of practice now. So A, we've got 18 divided by 9 times 2. So we've got no brackets, we've got no exponents, so we're up to multiplication and division, remembering that they're equal, and so we could just perform it left to right. And so ultimately we go 18 divided by 9, so then we can simplify that into 2 times 2, so we get 4. For B, we look and it's the exact same problem, we've just flipped the multiplication around. And so now we're saying 18 times 9. And so we've got 162 divided by 2, which will then equal 81. And so very, very different answers. So now we've got 18 divided by 6 plus 4 times 5 minus 2. And so I won't rewrite this one, but I will write an equal sign underneath. And so the first thing we want to look for is, are there any brackets? Well, there are in this one, so we want to simplify the brackets first. And so we'll rewrite the rest of the expression. And 5 minus 2 will be 3. And so now there's no actual more simplifying. Even though we still have a bracket there, we don't actually need the bracket. I'm just using it to represent multiplication. And so if you feel more comfortable putting a dot there once that bracket's dealt with, that's fine too. But now we look, okay, we don't have any more simplification in the brackets to do. And so we're just going to move left to right, looking for multiplication and division. And so there's 2 things we can do here. We can do 18 divided by 6, which equals 3. And then we can do 4 times 3. So we get 12. Then we're at addition and subtraction, and there's only one thing left to do here. So we go 3 plus 12, which is 15. Next up, we've got 5 plus 2 cubed plus 3 times 6 minus 3 times 4 minus 2 in brackets. And so, looks a bit tricky. The main thing I want you to remember here is that we're working on the innermost bracket first. And so we'll rewrite everything except for the internal of the innermost bracket. And so now 4 minus 2 will just be 2. And so we've simplified a little bit. Now we've still got some simplification to do in the brackets, so that's what we'll be focusing on next. And so now, what do we do? Do we do 6 minus 3? No, we've got to look and we've got to do our multiplication and division first. And so we've got 6 minus 3 times 2. And so we've got 6 minus 6. Now, we still have more simplification to do in the brackets. And so we'll rewrite the same thing again, ensuring that we're following BOMDAS or PEMDAS. And so we've got 3 times, and now 6 minus 6 is equal to 0. And so now we want to look at our exponents. And so we've got 2 cubed, so we can rewrite that. I'm not going to expand it, but if you want to expand it, you could go 2 times 2 times 2. I happen to know that it's 8, so I'm just going to rewrite 8. But if you need some more work on that, I do recommend going and having a look at some more practice examples. And so I'm also going to double up now rather than writing it again, because I can see 3 times 0. And so 0 times anything is itself. And so there's nothing there. We don't need to write anything there because it's just going to be 0. And so finally, we've just got 5 plus 8. And so we end up with 13. So this whole expression can just be simplified to 13. All right, so now simplifying 2 cubed plus 3 to the 4th power divided by 3 minus 5 squared. And so this one looks a little bit trickier. There's no brackets, so we don't need to worry about that, but we do need to deal with the exponents first. And so we really should probably expand this one so we can see what's going on. So I'm just going to rewrite this in expanded form. So we've got 2 times 2 times 2, plus, and then there's 4 3s. And then we've got divided by 3 minus 5 times 5. And so now we're looking, we don't have any more exponents, we don't have any brackets, so we can work from left to right. So the first thing I see is the 2's, and so 2 times 2 is 4, times 2 is 8. And then we want to carry down this sign. Please don't make any sign errors. If there's a plus there, it's got to be a plus unless there's a negative around. We won't worry about that yet, but just it's good to get into the habit of just carrying down the sign. And so 8 plus, and now we're at the 3's. And so before we do 3 times 3 times 3 times 3 divided by 3, I want to think, what is 3 divided by 3? And I know this isn't working from left to right, but I think this is an important observation to make. So 3 divided by 3, it's equal to 1. And so really, what we're going to be doing is we're going to say 3 times 3, which is 9, times 3 is 27, times 3 is 81, divided by 3 is 27. And so we actually are doing an inverse operation here, which means we can just eliminate this. And so this will become just 1. And so it will be times by 1. So we won't need to write anything at all. And so really we can just do 3 times 3 times 3, which is 27. Now minus, got to carry this symbol down. And then we've got 5 times 5, which is 25. Now, going through this, do 8 plus 27, which is 35, minus 25, which is 10. And so ultimately this whole expression simplifies down to 10. So that's the end. There was a fair bit of content today, but we've gone through some really fundamental things. So the main takeaways from this video are really BOMDAS and PEMDAS and the order of operations. Simplifying being getting everything down to its most fundamental parts, so simplifying all of the math possible. Then we were also talking about expressions and equations, and so the difference of those being the equal sign, and that's a really important part too. Inequalities and equalities we touched on, so getting comfortable with using those comparative symbols to compare different expressions in algebra will be important. And then back at the start, we spoke about variables and how they actually represent some potentially changing quality. All right, we'll see you in the next video.